Alright. Good morning, everybody. Welcome back. Okay, so for today, our goal is to continue what we started on Monday. So chapter number 3 is basically stoichiometry. And for this chapter, the goal is to predict amounts or that's going to be produced or it's going to be needed in a reaction. And the last thing we talked last time was regarding the different types of chemical reactions. So we can have 4 basic different types of reactions: combination, elimination, single displacement, and double displacement. Okay? And I gave you some examples regarding each type of reaction. Okay, very good. So let's move on to a new topic. Okay. So I would like to start talking about mole. And let's start with a very simple example. If you get 1 grain of coarse sand, that will fit on your fingertips. Okay? Very small grain. However, 1,000 grains of coarse sand that will fit on your palm, on the palm of your hand. And if we get 1 million grains of coarse sand, that will fit on top of the table. We humans are not capable of manipulating individual atoms or molecules in a regular manner. Okay? So therefore, we always need to work with a massive amount of atoms. Because atoms are very small, we need a huge amount of atoms to be capable of manipulating them. And this huge amount is defined as the Avogadro's number. And by definition, this number is 6.022 times 10 to the 23rd power. Okay. So every time we have 6.022 times 10 to the 23rd entities of stuff, we call it 1 mole. Moreover, the symbol for mole is mole, without the E at the end. Thus, you can have 1 mole of anything. 1 mole of eggs, 1 mole of atoms, 1 mole of dollars, or 1 mole of shoes. In all those cases, it means you have 6.022 times 10 to the 23rd entities. Okay, so try to look at the mole as a simple conversion factor. 1 mole is always equivalent to 6.02 times 10 to the 23rd. Let's take a look at an example here. For an adult, the little dose of arsenic is around 1.33 times 10 to the minus 3 mole of atoms of arsenic. How many atoms of arsenic are in the dose? And here, the Avogadro's number is 6.02 times 10 to the 23rd. Okay, so again, look at mole as a simple conversion factor, and whatever you fill in this gap here, it's going to be the same thing in the second gap. Okay? So we are talking here about atoms of arsenic. So that's what's going to fill our gap. Okay? So let's build first the conversion factor. Very simple here. 1 mole of, in this case, we are talking about atoms of arsenic. So that's what's going to go in the gap. And this is equivalent. Replace mole by the Avogadro's number, 6.02 times 10 to the 23rd, and then use the same thing that you used in the same gap, in the first gap. Atoms of arsenic. Okay, so knowing the conversion factor, now if you have the number of moles of atoms, you can find the other part of the equation. So there are a lot of ways to solve this problem. The one I like is to build 2 columns, and we are going to establish a proportion. The left column is going to be everything related to mole that we have in the problem. So we know that 1 mole is equivalent to 6.02 times 10 to the 23 atoms. And that's going to be our second column. And now we are going to divide both sides. The problem is asking about 1.33 times 10 to the minus 3 mole. How many atoms are there? So it's always a simple proportion. The first line is your conversion factor, or what you know, and your second line, there is one information that was provided by the problem, and the other one is what you are looking for. To solve any kind of proportion, we can do cross multiplication. 1 mole times x equals to 6.02 times 10 to the 23rd atoms times 1.33 times 10 to the minus 3 mole. Let's write all the units, and then we can figure out the unit for the answer. So once we have this equation, we have to isolate x. Let's send 1 mole to the other side, doing a division. 6.02 times 10 to the 23rd atoms times 1.33 times 10 to the minus 3 mole divided by 1 mole. Mole on top and at the bottom, you can cancel. Therefore, here 6.02 times 1.33. That's going to be 8.01. When you are multiplying powers, you keep the base and add the exponents. So therefore, this is going to be 8.01 times 10, 23 minus 3, 20 atoms. Okay, so using this strategy, it might take a little longer to solve the problem, but I'm pretty sure you're going to be able to solve any problem this way. Okay, very good. So let's see here the second example. Now attention, if a sample has 3.5 times 10 to the 5 atoms of sodium, what is the number of moles of atoms of sodium in this sample? Okay. So now I'm giving you the number of atoms, and the question is asking the number of moles. Okay, so just the opposite than what we did in the first example. So let's think about this problem for a minute, and then I will solve it. Okay, so we can follow a strategy. So now we are talking about atoms of sodium. So therefore, same thing here, let's build a conversion factor. 1 mole of atoms of sodium. Replace mole by 6.02 times 10 to the 23rd, and we are still talking about atoms of sodium. Okay? So same thing, first column of the proportion, we are going to input all the information in mole, and the second column, all the information in atoms. First line is exactly the conversion factor. Okay. 1 mole is equivalent to 6.02 times 10 to the 23rd atoms. I don't know the number of moles in 3.5 times 10 to the 5th atoms. Each simple proportion, whatever happens in one side has to reflect on the other side. Cross multiplication. So let's work with the fraction here. 6.02 times 10 to the 23rd atoms times x equals to 1 mole times 3.5 times 10 to the 5th atoms. Let's isolate x. That's going to send 6.02 times 10 to the 23rd dividing. So we will end up with 1 mole times 3.5 times 10 to the 5th atoms divided by 6.02 times 10 to the 23rd atoms. Let's check the units. Atoms on top and on the bottom, we can cancel. So our answer is going to be in mole as expected. So here we have a division of powers. So keep the base and subtract the exponents. So 3.5 divided by 6.02, according to my numbers, is 0.58. And attention here with the power. Keep the one on the top and subtract to the one at the bottom. So therefore, x is going to be 0.58 times 10, 5 minus 23 minus 18. Don't forget the unit, mole. You can express a little better the result, moving the decimal point to the right side. And that's going to be 5.8 times 10 to the minus 9 mole. Okay, so, and that's how you are going to convert from mole to atoms or vice versa. So always think about the conversion factor, view the proportion, and then solve the proportion. And every time we are talking about mole, you can replace mole by 6.02 times 10 to the 23rd. Okay, very good. So let's move on to the next concept here, molar mass. The molar mass is simply the mass of 1 mole of atoms, or 6.02 times 10 to the 23rd atoms. And its unit is grams per mole, or also represented by grams space mole to the -1. And the value for the molar mass, it will take into account all the isotopes of the element, and it's going to be found here in the periodic table at the bottom of the box for each element. Okay. So you can always refer back to the periodic table, and this number here at the bottom, that's going to be exactly the molar mass for the element. For example, the molar mass of potassium is 39.098 grams per mole, and that means 1 mole of potassium weighs 39.098 grams. And in this mass, you have exactly 6.02 times 10 to the 23rd atoms of potassium. Okay, so we are going to expand a little bit our conversion factor. We know the equivalence between mole and number of atoms. And now we know that 1 mole is equivalent to the molar mass of the element. All right. Very good. Okay, so let's solve one example here, then I will show you the logic. Okay, the example, consider a sample that has 1 gram of potassium. First question is, how many moles of potassium are in the sample? And second part of the question, how many atoms of potassium are in this sample. The problem provides a couple of information. Molar mass of potassium 39.098 grams per mole, and Avogadro's number 6.02, and then choose the 23rd. Okay, so I'm going to write a big conversion factor that's going to correlate mole, atoms, and molar mass. So if we have 1 mole of potassium, this is going to be equivalent to 6.02 times 10 to the 23rd atoms of potassium. And now we know that 1 mole of potassium is going to weigh 39.098 grams. Okay, so this information here comes from the molar mass of PL. Okay, so now we have a big conversion factor that has 3 components, and you can use any 2 components in this conversion factor, depending on what the problem provides to you. The first part of the question asks the number of moles in 1 gram. So I'm going to use the parts of the conversion factor that correlates mole and mass. My first column here, mole, second column, mass. From the conversion factor, we know that 1 mole of potassium weighs 39.098 grams. And the problem is asking us 1 gram of potassium, how many moles? So now we end up with a simple proportion. Whatever happens on the right side, it has to happen on the left side. Cross multiplication, 39.098 grams times X equals to 1 mole times 1 gram. Let's isolate X, sending 39.098 dividing. X is going to be 1 mole times 1 gram divided by 39.098 grams. Cancel grams with grams. The unit for our answer is going to be mole. Therefore, number of moles is going to be 0.026 mole. Or, if you want to put this result in scientific notation, 2.6 times 10 to the minus 2 mole. Right, so pay attention to the number of significant figures. So it's multiplication and division, and our limiting number here is 2 digits. Therefore, your result must have 2 digits. Okay, so now the second part of the question, how many atoms of potassium are in this sample? Okay? How many atoms of potassium in 1 gram of potassium? So we can solve this problem in 2 different ways. The first one is to correlate atoms with mass, and that's a direct correlation, and the one I recommend. The second one is to use the result you got from the first part, mole, and correlate mole and number of atoms. I do not recommend you to use this correlation because if you are wrong in the first part and you use wrong results, you are going to be wrong in the second part. Okay? So therefore, I'm going to correlate atoms and mass because that increases my probability to get a correct result. Okay, so now let's use the second and third part of our conversion factor. First column, atoms. Second column, mass. From the conversion factor, 6.02 times 10 to the 23rd atoms. That's equivalent to the molar mass, 39.098 grams. Let's divide both sides. And the problem is asking us the number of atoms in 1 gram. Okay. So again, this is a proportion. Everything that happens on the right side has to happen on the left side. Cross multiplication. For 9.098 grams times X has to be equal to 6.02 times 10 to the 23rd atoms times 1 gram. Let's isolate X. We are going to send 39.098 dividing. And ending up with 6.02 times 10 to the 23rd atoms times 1 gram divided by 39.098 grams. Grams with grams we will cancel. Our answer is going to be given in atoms. Okay? So therefore, the number of atoms in 1 gram is going to be according here with my numbers, 0.15 times 10 to the 23rd atoms, or if you want to move the decimal place 1 spot to the right, 1.5 times 10 to the 22. Can you or your mask? Sorry. Thank you. Any questions regarding mole atoms or moles? All right. There are no questions. Yes.
So a mole is the minimum amount of atoms that humans can manipulate. You were talking about the palm of your hand. Is it just any manipulation, or is it like physically, like manipulate with your hands?
Well, not the minimum amount, but an amount that we can manipulate. Okay.
Do different atoms vary in the minimum amount that we can?
No, one mole is always 6.02 times 10 to the 23rd. And the limitation on the manipulation then is going to depend on density of atom and your precision that you are looking for. So in the lab, you are able to weigh 1 milligram of atom. Okay. So that's not much. Okay. So I still need to have a lot of atoms there. All right. Okay. So we talked about molar mass of an element. Now let's move on to a more complex system. Let's talk about molecular mass. When elements combine to form compounds, there is no point in talking about individual atoms. Okay? Now we need to talk about the compound as a whole. The molecular mass of a molecule is simply the mass of 1 mole of molecules, or 6.02 times 10 to the 23rd molecules. And its unit is grams per mole, or gram mole to the -1. Okay, so now we are not talking about individual atoms, but we are looking at the molecule as a whole. So let's, for example, take a look at water. Everybody knows the formula of water, H2O. Okay. So for water, we have 2 atoms of hydrogen, represented here by the subscript, or 2 moles of atoms of hydrogen, and 1 mole of atoms of oxygen. Okay. So now imagine that I toss 2 moles of atoms of hydrogen and 1 mole of atoms of oxygen in a bag, and I want to know the molecular mass of the compound or the weight of the bag. Okay? So therefore, each individual atom will contribute to the whole mass, and we know from the periodic table that the molar mass for hydrogen is 1.01, and for oxygen is 16. Therefore, the molecular mass for water is going to be the sum of the contribution of each element to the compound. 2 moles of hydrogen, each hydrogen is 1.01, and 1 mole of oxygen, which is 16.0. Therefore, molar mass for the water, that's going to give us 18.0 grams per gram, or grams mole to the minus 1. Okay, so every time you talk about a compound, the molecular mass is going to be the sum of each individual contribution. Okay, pay attention to the number of atoms for each element, and that's going to be represented by the subscript. Okay, so now the problem starts to get more complex. Now we know that 1 mole of molecules of water, it has 6.02 times 10 to the 23rd molecules of water and weighs 18.0 grams. Okay? So pay attention what the problem will ask. Okay, so let's go over one more example. Let's start it. We will finish for today. For this example, consider a sample that has 2.5 grams of calcium fluoride. First question, what's the formula of calcium fluoride? B, what's the molecular mass of calcium fluoride? Let's limit to 3 6. How many moles of calcium fluoride are in 2.5 grams? And how many atoms of fluorine are in a sample containing 2.5 grams of calcium fluoride? From now on, the problems start to get more complex. And as I told you, if you are not sure about previous concepts, go back and make sure you know them. To start the question, you have to know the formula of calcium fluoride. You have to remember nomenclature. You have to remember how to get the formula from the name. Let's think about this problem for a couple minutes, then we will solve together. Okay, so let me do the first two items in this problem, and then we will wrap up. So everything starts with the formula of calcium fluoride, right? Calcium is in the group 2, therefore it's a 2 plus charge, and fluorine right here on top of the group 17, so therefore -1 charge. So we're going to combine cation with an ion, cross the charges, and that will give you the formula for calcium fluoride. It's CaF2. Now that you correctly identified the formula, next step is quite simple. Let's determine the molecular mass of calcium fluoride. 1 atom of calcium, 2 atoms of fluorine. The molecular mass for calcium fluoride is going to be the mass for calcium. So let's limit this to 3/6, 40.1. Plus, attention here, we have 2 moles of fluorine in the formula, 2 times the mass for fluorine, 19.0. Therefore, molecular mass for calcium fluoride is 19 times 2 plus 40.1, 78.1 grams per mole or grams mole to the minus 1. Okay, and then we are going to use this number for C in part of D items. Okay, very good. So this is good enough for today. So let's wrap up. And then on Friday we have the classes. The rest of the week.
Bye.